I'll start the recording.
I got it.
Oh, you're doing it. You got it. Okay.
Thanks, Doug.
Yeah. So welcome everybody. Tonight is the June 9th, 2022 AFSig meeting. And tonight we've got Stephen Ferris giving us a talk on the history of large telescopes, famous large telescopes. So I'll turn it over to Mr. Ferris.
All right, give me just a second to share the screen and get the file started. Okay, we're good to go for there. I'm going to call this. I'm having a little bit of internet issues tonight, so if things get a little bumpy along the way, I apologize beforehand. Hopefully everything will work relatively smoothly throughout the presentation. So when I was asked to put this together, the idea was all large telescopes or all giant telescopes. And what I discovered is there's so much out there that it's not practical to try and get this into 1 hour and try and talk about the modern ones. So I decided to do is focus mostly on the historical telescopes that run from Galileo through the Palomar Observatory, the great 5-meter that they have up there. Most of these telescopes some of the telescopes that we see no longer exist. There are artifacts of some of them. Some of them do exist, but most of them are no longer used as research instruments. The exception would be the Palomar scope itself, which they're talking about eventually closing down and possibly, but there's no firm plans for that as far as I know right away. We'll talk a little bit about Palomar and why it's a good site and why not such a great site as we go through some of the slides. So I'm going to just start with a picture and a question. You don't necessarily have to answer it, but just get to think about it. What is a giant telescope? Well, this is the 61-inch up on the top of Mount Bigelow. And at the time that it was created, it was not a giant telescope, but if it had been built 50 years earlier, it would have been. So one of the things to think about is what constitutes a giant telescope very much depends on the time and the capability of the technology of this particular era. So I kind of had a broad definition of giant. We think of giant as giant in aperture, but I'm also going to be talking about just giant in size because some of the scopes we'll look at are in fact very overall mass and size because of the limitations, again, of the technology of the time. So this is kind of a fun one to start with. Is it a giant telescope? Is it not a giant telescope? Well, by today's standard, it barely qualifies as a research telescope, as 61 inches is fairly small, but by a lot of the standards that we're looking at, it actually is a fairly large telescope. So things that we're going to talk about are some of the giant telescopes, historic telescopes, really from about 1609 to about 1990, although the story really ends with Palomar, which became functional, I believe, in 1948. We're only going to be looking at optical telescopes. That might be a fun presentation for another night to start looking at maybe infrared telescopes. And of course, a lot of those cross over into optical telescopes, but also some of the X-ray and radio gamma ray telescopes that are out there now, most of which in the high frequencies are located in space. Talk about some different telescope designs. I'm assuming almost everybody here is familiar with the basic telescope designs, refractors, reflectors, Casegrins versus Newtonians and things like that. But I'll go into that a little bit in case anybody's not clear on that, as well as some of the challenges involved in creating giant telescopes. Like all my presentations, they'll have lots of pictures and a little bit of history. And one thing I need to point out is we're only looking at ground-based telescopes tonight. Obviously, there were no space telescopes in 1948. The space had not yet been entered by humans. That would take a couple more years. But there is the whole story of space telescopes, which is much more recent. Until recently, those were all much smaller in aperture than the scopes we'll be looking at tonight. And there were reasons for that that might make a great presentation for AFSig for another evening. So naturally, any discussion of telescopes has to begin with Galileo. Well, Galileo did not invent the telescope. The information I have said Hans Lippershey. He was a Dutch optician who started manufacturing telescopes as spyglasses. Of course, the Dutch at the time were major nautical power. There was a lot of interest in navigational equipment and also land for military purposes. And so that was the original purpose of the telescope. It might have been earlier versions, but there's not recorded information about that. Galileo may not have even been the first person to point a telescope up. There are rumors of other people possibly having done that, but he was the first to publish. So as often happens in science, it says publish or perish, and if you get scooped, too bad for the loser. He was the first one to publish in the Starry Messenger. I'm not very good with my Latin, so I won't try and pronounce the name that is actually under, but he was the first person to record that he was doing that. And there were letters that he sent out and information to various friends even prior to that of what he was doing. The telescope design that he used was very, very simple. It was essentially a convex lens up in the front and a concave lens in the back that formed the eyepiece. And it was not a very good telescope, but by the standards of the day, it was the largest that had been produced yet, simply because nobody had built anything bigger. This is on the left, I believe, is a decorated version of his original telescope, and on the right is a mock-up. This is a modern reproduction based on what they believe his original telescopes look like. A couple of things to notice about this is obviously they were very small aperture to begin with. And he also, you'll notice that ring of either wood or paper that he inserted on the front of the lens. That was to stop it down. And the reason was that the telescope design that he was using had so many inherent aberrations, chromatic being the biggest one, that he really needed to stop down the lens in order to deal with that and form an effective image. And so the actual aperture of this telescope is tiny. It's obviously smaller than a modern binoculars, and so it was not to have a large aperture to work with. But he was able to obviously see the famous things that he was able to see, the details of the moon, including the craters, the phases of Venus, and the moons of Jupiter. He never clearly figured out what the rings of Saturn were. He described them as ears, but they would take another few decades to figure out we were looking at rings, and we'll talk a little bit about that in a minute. So problems with the Galileo Lippershey designs, there's multiple aberrations, especially chromatic. In order to compensate, he stepped on the telescope. Another solution was to create a super long focal length for very small apertures. And this tended to correct a lot of the aberrations, but it did not take care of them completely. There were still problems with the telescope. And the solution that they came up with for the first 50 to 100 years was massive assemblies for very small optics. They were not able to produce very large telescopes in terms of width, but they had very long focal lengths, which required huge mechanical apparatuses to be able to mount. So this was what the kind of telescope that Christian Huygens, famous for discovering Titan and also a very known astronomer of his time, was able to use. As you can see, is basically using a ship mast, and at one end is the observer, and at the other end is a small lens. By our standards, probably not much bigger than an 80 millimeter refractor today. You know, he may have gone up to 2 or 3 inches at most, but there wasn't certainly very big optics by today. This is one of the different arrangements that was used at that time to produce a very small optic with a very big telescope. I consider it giant simply because having to mount it onto a mast similar to a ship was a pretty impressive thing. There's also the aerial telescopes that were used. These were a slightly different design. In this case, you would have a 3-inch lens Up at the front, this thing in the center is a mock-up. It's a modern replica of the device, whereas on the left is a historic picture or engraving of the apparatus as it was existed in the mid 17th century. And as you can see, basically what you did is you pointed, or you had your assistants point the telescope at your object as best you could, and then on the ground, you had a lens, and you tried to match up the lens within your hand with the lens on the objective up on the top of your mast. And coordinating this was obviously not an easy thing, especially since the sky was, the objects were, rotating or seemed to be rotating. And so you can imagine there's probably some very frustrating evenings spent by people like Huygens and Cassini playing with these lenses, trying to get an image that could be usable. I believe the image on the right is blocked by our screens, but I believe that is a original of one of these aerial telescopes. So by focal length, these were massive. And by aperture, they're very small. So you get to decide if these were large telescopes. By the standard of the day, though, they were as big as they could build, because anything bigger that was shorter in focal length would not be effective in forming a real image. It would simply be either too blurry or too much chromatic problems with it. So evolutions in telescopes, the reflector comes along in the second half of the 17th century. By the second half of the 17th century, refractors were showing some of their inherent problems. There were corrections, but they came on much later, the beginning of the 18th century. So the new solution that was independently come up, or sort of semi-independently invented by three different designers, was a reflecting telescope. So instead of using lenses up at the front, they would use a mirror or multiple mirrors in order to collect light and form an image. And so we obviously lenses like eyepieces would be attached to the back end of these things, but the main collecting system was a mirror system rather than a lens system. Reflectors mostly get rid of chromatic aberrations unless there's, in fact, I usually always do, but they have some aberrations of their own, such as spherical aberration and coma. Anyone who's worked with the Newtonian even today design knows that coma is part of their design. And if the mirror is not precisely made, which was very difficult to do way back 3 centuries ago, there would be some spherical aberration. And of course, if the mirror wasn't perfect, there would be the kind of aberrations we see in reflecting telescopes today. So it wasn't a complete solution, but it was a better solution than refractors, at least for a little while. So there were 3 different designs that were proposed at roughly the same time by James Gregory, Isaac Newton, and Julian Cassegrain. And of course, I'm probably butchering his name pretty badly. James Gregory was a Scottish optician and inventor, I believe, who came up with what was called the Gregorian design. He did it mathematically and basically on a piece of paper. Isaac Newton, of course, is well known as probably the greatest astronomer of the 17th century, or the greatest scientist of the 17th century. He did some astronomy, but that was not his main area of focus. He was primarily a physicist and mathematician. And then we have, of course, today with the Cassegrain design, which of course was modified in the 20th century to include a corrector plate at the beginning to become our Schmidt-Cassegrains, which we use all the time now. There are other Cassegrain designs out there, including just a pure Cassegrain, which can be used as well. It has some aberrations of its own, so it's not quite as popular as some of the other designs without the corrector plate. Gregory and Cassegrain never actually built their telescopes as far as anyone knows. They simply designed them based around mathematical principles, and basically they were paper telescopes. Newton only built one small one that we know about. It was a 1-inch prototype. He never necessarily had built anything bigger that we're aware of. The problem was for all 3 was how to create parabolic mirrors. Spherical mirrors to this day are much easier to make. That means that the shape is the shape of a sphere. The problem is with that is that the light comes to focus at different points if you're making a spherical mirror. And of course, that is a real problem if you're trying to form an image. problem with parabolic mirrors is they're very hard to shape and very hard to polish and shape to that specific design. And that would become a problem for the telescope manufacturers in the 18th century, was how to get a nice parabolic shape for their reflectors. Good opticians were able to do it relatively well, but anything that was poorly made would become a problem. And of course, they did not think of the corrector plate until the 20th century, when they started making Schmidt telescopes. That was something that would take a couple more centuries and is sort of beyond the purview of this presentation, because most of them were never giant. So this is the different reflecting telescope designs. I'm going to have you ignore the one on the right, which is the code focus. That came a little bit later, but the simplest system is simply a prime focus with the mirror in the back, and then you put your eyepiece up in the front. People did try this, and I'll get to that in a few minutes. The secondary mirrors system was either the Newtonian focus or the Cassegrain focus. The Newtonian, of course, has a secondary mirror which bounces the light off to the side. This is a very familiar telescope to all of us. And then the Cassegrain focus is in the back. One of the things that has to be emphasized, unfortunately our pictures are in the way, is the difference between a Cassegrain focus and a Gregorian focus. The Cassegrain focus uses a convex secondary, and the image comes to a focus behind the telescope. The Gregorian uses a concave mirror as the secondary. The image comes to a focus before it and then again behind it. And so the result is multiple I'm forgetting the word, but the image is both upside down and backwards in every way you can think of it with a reflecting telescope. Refractors simply reverse an image. Cassegrains and Newtonians do other things with it, which are inconvenient if you're trying to point the thing in terms of direction, but that is a common problem with any kind of reflector.
Stephen,
yes,
sorry.
Steve.
You're butchering the name to the point where I can't, it hurts my ears. It is Cassegrain, not Cassegrain. It's Grain. I looked up his last name.
Okay.
Cassegrain.
Okay, Cassegrain. All right. So 18th century through the 19th centuries was the first age of reflectors. And there's a second age going on now. In spite of the aberrations inherent to reflectors, telescope builders quickly picked up on the fact that large reflectors were much easier to build than large refractors. Now by big, we'll have different definitions of big as we go along. At first, they were fairly small by modern standards, but they became bigger with time. And there was a key difference between historic and modern reflectors. Most of the historic reflectors that we'll talk about had speculum mirrors. They were made of metal, they were not made of glass. There were reasons for this, largely because it was hard to create glass blanks that big, and also because they're were easier to make the metal ones at the time. Not that the big ones were easy to make either. Speculum is an alloy of copper and tin, so it's similar to bronze, but it has a slightly different mix of the metals involved. Of course, there's problems with the speculum mirrors. These are some examples of speculum mirrors from the 18th century. From my research, it seems like speculum was something that was commonly used for mirrors at that time anyway. The glass making technology not developed to the point where the large mirror blanks could be manufactured, and it was easier and more practical to make them out of metal. The problems were that speculum tarnishes, so after a few months or a few years, the mirror is basically useless unless you can find some way to repolish it. And then it also has poor thermal properties. Any kind of metal mirror is not going to be as stable thermally as glass will, and as a result, you get the kind of wobbly image that we sometimes see in our telescopes, but potentially much worse. And so that's a common problem with these mirrors. But given the technology today, they were a better solution. James Short was a optician and telescope manufacturer, I believe also Scottish. He picked up on the idea of the Gregorian design and made several Gregorians up to 24 inches. These telescopes were obviously not very big by our standards. They probably cost a fortune in their day and are now, as you can see, museum pieces. I don't know if anybody actually uses them anymore, but they are, for their time, the James Short's telescopes up to 24 inches were the largest telescopes of their day. William Herschel is, of course, probably the person most closely associated in the 18th century with making reflecting telescopes. He's best known for discovering Uranus, but he was originally a musician, and he was also fascinated with astronomy. And he built what were then the largest telescopes on Earth. First at 24 inches to match what James Short was doing, and then his 48-inch telescope. We call it 48-inch today. In the past, telescopes were defined by their focal length, not necessarily their aperture, because that was what was the focus of the time. Obviously, they knew that a bigger aperture was probably better, but when they talked about telescopes, they would talk about the focal length, which in this case was 40 feet. It was he ground and polished his own speculum mirrors. Interestingly, Uranus was not discovered with his 48-inch. It had been discovered prior with a much smaller telescope. He got into the larger telescopes a little bit later in his career. He used the largest telescopes to catalog over 1,000 objects. And as Doug will point out, that's a major observing project for the astronomical, Doug are going to kill me, but I'm blanking on the name of the Astronomical Society.
Astronomical League.
Thank you. Astronomical League has the Herschel 400 and the like. And as I said, the Uranus was discovered on a small telescope, so it wasn't discovered with the 48. So this is the diagrams of the 40-foot telescope, the 48-inch that he built. As you can see, it was quite a contraption. They really did not have an effective way to rotate this assembly. It is an alt-az mount, or an altitude azimuth mount. It is very complicated looking, but actually works fairly simply. The telescope was made of, I believe, steel or iron, the tube, and the mirror was speculum again. And it can't really rotate very well in azimuth, so it can't turn left or right. It also had fairly limited abilities in altitude, simply because you had to crank this thing up. They didn't have electronic motors or steam engines at the time. They were inventing the steam engine roughly at the contemporary, but they hadn't attached any to telescopes yet. I don't think they ever did. That would create a lot of problems, but you could crank it up. And interestingly, I'll come to the focal design on this in just a second, but as you can see, the observer, who is usually William himself, would sit in a cage hanging off the front of this thing. And typically what they did in that era, what he did in that era, was the telescope would be pointed at a certain altitude, and he'd wait for objects to cross into the field of the view of the telescope, and then he'd call out the name, the description, and the location as best he could to an assistant, who was often his sister Caroline, but not always. I'm sure he had other assistants as well. And that was simply the way they did the observing. That was because of the limitations of hauling such a big telescope around. That was the best way that they could do it. This is an image of the actual mirror. As you can see, highly tarnished by any standard. This is the 48-inch mirror that he built. At his time, Herschel was considered an excellent optician, one of the best in Europe, and so he was able to fashion a mirror that was fairly accurate. Obviously had all the limitations of a metal mirror, again, the temperature adjustment problems, but it was any of his telescopes were considered fairly good, even though his formal training was in music. So it was a good telescope for the time. the 40-foot work. This is a model created today. He had an interesting optical design. This was not a Newtonian. It was actually a design that he didn't necessarily create, but sort of adapted from a Newtonian. It's actually a prime focus telescope where he would, except it was it came to a focus off to the side towards the bottom of the front of the tube. He would have an eyepiece and stare down the tube of the telescope to the mirror. There would be a lens there, an eyepiece or a lens at the top that he would look to, and he would look down onto the mirror as the mirror collected behind him. Obviously, he would not be standing in front of the whole mirror; only his head would be poking up from the top. But this is actually how he did observations. Was a cage hanging off the front of this thing, and it was interesting because when I started this, I assumed he was using a Newtonian design, and he was off to the side. He was actually up at the front of the thing. Pointing that having somebody record his observations as they went past him. So not a very comfortable way to spend an English evening when it was clear, which is a problem as well. But it was certainly a little bit daring to be hanging 30 or 40 feet off the ground on one of these things. There was another platform below him if he ever fell off. I'm not sure if he ever did, but certainly sort of a daredevil way to observe. But it was the best they could do in the time. Remember, he didn't go with the Gregorian design, and there would have been problems mounting that, and so that was what he had to work with. The next giant telescope to come along to exceed Herschel was the Leviathan of Parsonstown. This is a picture of the structure at Beer Castle. I do not know if the tube itself is a reconstruction or if that's the original tube. The image information I got didn't say, but it too was a slightly different design from what Herschel did. This was a true Newtonian in that the optics pointed the light out to the side where there was an eyepiece. It was a very large framework. The side parts are stone, and then there was a wooden and metal structure that they used to observe and guide the telescope as well. This one too, as you can see, is obviously not something you can rotate in azimuth. Those are stone walls. There's no way to turn the thing right and left as you can do with a big telescope today. It could be moved again in altitude, so you could point it a little bit further up and a little bit further down. The telescope was built or commissioned by William Parsons, 3rd Earl of Ross. He was a wealthy English-Irish nobleman. He was Irish by nature, by birth, but he was also a large landowner at the time, and he used his wealth to commission a telescope. He was kind of on the border between an amateur and a professional. He was formally trained in mathematics. His degree was in mathematics, and I do not believe he ever achieved a PhD, but he did have some formal training in that. He commissioned the telescope to, of course, exceed what Herschel had done. And the telescope had a 72-inch speculum mirror. It was built again at Beer Castle between 1841 and 1845. The construction was sadly hampered by the Irish potato famine. There were obviously a lot of disruptions going on in Ireland at that time, and it made it very difficult to complete the telescope. The mirror at the time weighed 5 tons. Which is obviously something that makes it very difficult to move around, given that the contraptions were basically just wooden pulleys and things like that made it move. Again, had the Newtonian design. The superstructure, the stone walls that you see on the side of the picture, still exist, but the telescope sadly does not. And I was unable to find if the mirror exists to this day. Yes, Douglas.
I just sent you a chat thing, but that's okay. The tube still exists. It's on display at the castle.
Okay, I have not
It's
been
lying flat on the ground.
Okay, so the tube still exists, is not in place. This was the largest telescope until 1917, and we will get to the point where the next biggest one comes along. The Leviathan of Parsonstown had some limitations. Obviously, it couldn't track in azimuth. The other problem was the Irish weather. Famously, Ireland is probably not the best place on Earth to do anything other than radio astronomy. And so although he had a very nice telescope, he wasn't necessarily able to do a whole lot with it because the Irish weather didn't really do very well for telescopes. There were a lot of cloudy nights, a lot of rainy nights. And so and of course England isn't much better for Herschel, so I don't know if he had better luck than Parson did. But in this case, it was not considered, other than a technological triumph, to be necessarily the greatest scientific achievement. He did, however, make a few important findings. I'm going to go back one step. He was able to trace out the spiral nature of some of the spiral galaxies, particularly M51, and he was able to show, he was almost able to resolve stars in the Andromeda, at least that's according to the story that I read, but not quite. And so he did make some achievements, but it was not considered a major success on the fact it was just the biggest telescope on Earth. Meanwhile, changes are coming back to the refractors. During the early 18th century, they begin to develop the concept of achromatic refractors, or achromatic refractors. I'm probably butchering the name both times, but it was originally achromatic. The idea was to remove the chromatic aberration. The way that they did this was, first of all, two lenses up at the front, a doublet objective, one made of crown glass and one made of flint glass. And they have slightly different optical properties. And when also the crown glass is convex, and the flint glass has a concave surface. The idea is that between the different shapes of the lenses and the different materials that they're made of, you roughly bring the different wavelengths to focus at the same point. It's not perfect, as anyone who's had a doublet scope, this is an achromat, today knows that there's a little bit of chromatic aberration with these things, but it is much better than the Galilean design that was being used at the time. The biggest advantage of this is you could now build bigger telescopes with shorter focal lengths. And so you do not need a whole ship sail in order to mount these things. That doesn't mean that they were small. It just means that they were not as big per unit of aperture as some of the scopes that had come before them. And so that really, along with it took a little while for these lenses to come into wide use while Herschel was developing his reflecting telescopes and the like. There were refractors out there, but it really was not until the late 19th century that refractors really came back into fashion again as big telescopes. And there was some smaller versions. Fraunhofer, and again, if I butcher his name, I apologize, is best known for the Fraunhofer lines in the solar spectra. He did discover that, or at least was the first to note it. But of course, Newton had discovered the spectrum and things like that much earlier than that, but he was looking at the sun. But he was also one of the great opticians and telescope builders of his day. And so he was primarily based in Europe, and so several of the observatories of the day sought out his telescopes. This was one of the larger ones. I believe it's either 6 or 8 inches. It's no longer in regular use, but he did make fairly large refractors for some of the European observatories. Again, these are considered classic telescopes. They were not necessarily the largest telescopes in the day in terms of aperture, but they were considered some of the best in terms of the optics. Refractors to this day have some very nice qualities, which is why we continue to use them as amateurs. Once you had corrected the chromatic aberration, they tended to produce a pretty nice image. And so in the second half of the 19th century, those advantages come into place. Fraunhofer was a little bit earlier. He was early 19th century. Yes, Doug?
I just wanted to mention, take a good look at that image on the left.
Mm-hmm.
It's got a weight-driven clock drive.
Mm-hmm. Yeah, and of course the mechanics were so precise that he could build these things so that they even without electricity, they were pretty precise in terms of their tracking. Again, one big caveat here is that photography wasn't really applied to telescopes until the second half of the 19th century either. There were problems, namely the biggest one being that they required very long exposures just to produce an image in full light. The early photographic techniques did not lend themselves very well to telescopes until the 20th century or the late 19th century. But visually, these were superb instruments and for their day. Obviously, a little bit of a chromatism at the time, but it was much better than what had come before. This is another, I believe it's an 8-inch scope. It may be, as you can see, the mechanics on these were spectacular along with the lens production. They were, again, happen.
I don't know. Okay.
Okay, not quite sure what happened there, but I hope the recording is a still are considered very good optic for acrochromats. Most are considered museum pieces. He not only built some small telescopes by our standards, this I believe is a 6-inch. Again, look at the mechanics on that. These are often have to be restored. Many of them were sitting in domes or in the basement of various observatories for decades, and then were refurbished according to the original standards fairly recently. But as you can see, when they're in good condition, original condition, they're beautiful instruments. I believe this was a 6-inch, but he made much bigger. He was mostly known for the quality of his optics, though. Rather, I believe that most of the tubes and manufacturer designs were actually, he would attach the optics to it later and also to the mounts. So this is where I have to make a slight segue to Percival Lowell, who is another who was a rather interesting character, who, of course, buys a very large Clark telescope. Percival Lowell was a amateur. And he's, of course, someone who's come up several times in our presentations on Mars, but he was an amateur from a very wealthy New England family who developed an obsession with Mars based on some of the findings that had come out legitimately from Schiaparelli in Europe. And he moves telescopes all over the country and gets involved with observing projects, I believe, all over the world. And eventually he wants his own big telescope. And so what he builds is still in existence today. It was at the time one of the biggest telescopes in the world, at least by refractor standards. It was a 24-inch Clark reflector at Lowell Observatory. This is quite a telescope. It still exists today. It is not used for science. It is used almost exclusively for public outreach. You can go there and visit the telescope. There are occasional nights where you can observe through it. As you can see, it was built inside a wooden dorm at Flagstaff. And the reason he chose Flagstaff was because it had fairly good observing conditions compared to his own native New England. And it was on a rail line where he could ship items out to the Arizona West and build his observatories there. It was not the first telescope that he built there. It was the biggest at the time. It's a 24-inch lens that he built, commissioned by Alvin Clark and Sons. is still considered a very good telescope. As you can see, and we'll talk about this later, it's beginning to see some of the limitations of large refractors at the time, one of which is 24 inches, but a very big telescope, all right? So it's got a huge tube. It's on a massive mount. Again, this was a mount that is very precise. I believe I didn't really find a lot of information about the mount itself, but the telescope itself was considered excellent at the time. And this is where he went and had his belief that he had seen canals on Mars. It is considered a classic, though, in terms of telescope design and telescope usage. Still one of the best large refractors out there. And like, as with any refractor, obviously he's viewing from the bottom. He'd have to get up on a ladder. They didn't necessarily have the floor that lifted yet, like some of the modern large telescopes do for observing. So it was somewhat precarious to use. But if you ever wanted to take the trip to Flagstaff, I have not. I unfortunately have not seen this before other than in pictures, but I would love to go visit it. Is quite an object to view. And this is an outside picture of the dome. It was constructed in wood. Probably has folks a little bit nervous today with all the forest fires that are so common in the modern era. If that forest fire were to come, and Flagstaff is forested, if a fire were to come through, there would be a serious problem. This is called Mars Hill, and it's his 24-inch Clark refractor. And the scope is named after Clark, not Lowell. Is that the right one? I'm sorry, I'm tired. But that is the Lowell Observatory Dome on Mars Hill. Also, another major construction by Clark was the 36-inch Lick refractor. This, again, at the time was one of the largest refractors ever built. It is, again, decommissioned for scientific use. There was talk about closing it down at one point. I believe it's now being used occasionally for observing nights and basically as a relic of a bygone era. Look at the size of that mount. This, I believe, is getting to the point where it's electrically driven. But for a 36-inch telescope, we're talking about a huge amount of mass. And yes, Doug.
It was not originally electrically driven. It had a clock mechanism that was driven by weights until the early 20th century.
Right. And the catch with it, of course, is this is something that was so precise you could maneuver it with a hand, but it was balanced so beautifully that you could do that. But it's a massive tube and a massive mount that was required to suspend it. Also notice the floor. I do not believe that they yet had the ability to raise that floor very far. So if the telescope had to be pointed towards the horizon, you had to get up on some kind of a ladder to do that. And so on the left, you see the picture of the gentleman, and it usually was a gentleman looking through the telescope tube at the time. Again, photography was just coming into usage in astronomy at this point. And so it was primarily at first a visual instrument. And at that time, until the 1870s or 1880s, there was not much photography going on, again, because of the problems with making exposures that required a fair amount of time. And we'll come back to that in a minute. This is a modern pictures of the 36-inch Lick. As you can see, it's still considered in fairly good condition. They do occasional outreach meetings with it. It's, I'm sure, been cleaned and restored at various times, but it was almost the biggest refractor ever built. That distinction goes to the 40-inch Yerkes telescope. Now, I'm fairly certain it is Yerkes and not Yerkes. The 40-inch Yerkes great refractor was a product of the late 19th century. This was the biggest refractor ever built. And there were reasons for that, which I'll go into in just a minute. This was built of all places, Wisconsin, which was probably not the greatest place to build it. It was built because it was convenient for the University of Chicago, and they built it on the side of the lake by Lake Michigan. Not necessarily the best spot even available during the day, but it was convenient for the owners of the University of Chicago to use it there. Again, a massive structure for unit of aperture. Look at the size of the mount. It's actually the mount itself is actually it's not. I wouldn't call them stories, but there's several different rungs there to get up to the top of it. In a massive construction. So really an achievement technologically. My information says that the lenses were created by Clark as well.
Yep.
And so it was in his time and still is the largest refractor ever built and mounted. Interestingly, there was a bigger refractor that was built for the Great French Exposition. It was always placed horizontally. It had a heliodstat. I'm probably butchering that word as well in the front. Heliostat, yes. And it was never considered a very good instrument, even though it was, I believe, 48 inches rather than the 40-inch Yerkes. Yes, Douglas.
This telescope is still used in a research capacity. It's still specifically used for proper motion studies because the lenses have never been removed from the tube and have never been changed in their position. So the photographic plates that were taken 100 years ago, 120 years ago with telescope are constantly being used for proper motion studies because there's been no change in the orientation of the original lenses.
The telescope itself, though, has been in some peril recently, in that the University of Chicago no longer uses it actively for research very often, and they didn't necessarily want to pay for it. And so there was, it does cost a fair amount of money to maintain the facility. Again, I have never been to Yerkes. It's in a beautiful spot on Lake Michigan.
I've been there. It is a beautiful spot.
It's a beautiful spot on Lake
and
Michigan.
I have looked through this instrument on an outreach night.
And they do use it for outreach, but it costs them a fair amount of money to do it. And so a few years back, University of Chicago, which is the owner of the instrument, was thinking about shutting it down completely and possibly decommissioning it entirely. They are now working on making it into an outreach instrument permanently, but possibly with University of Chicago funds, but there's still some debate about that. It does not look like this thing is going to be dismantled anytime soon, but at the same time, there has been a little bit of concern, especially among people who are telescope enthusiasts versus the university, which is interested in investing the money in more modern instruments and more modern projects. For the moment, it looks like it's settled. It's going to be used for the public, which is wonderful. You can still go see it as it is, and it is a beautiful instrument and its time, and really kind of a tribute to the manufacturing capability that was in the late 19th century America. It's one of the best of his class. Now,
the other thing about it, the National Science Foundation, like I said, is still doing proper motion studies with it. Is that light pollution doesn't hurt proper motion studies because all you have to do is take a picture of the star. You're not trying to get nebula or galaxies, so they're still using it, like I said, for the proper motion studies because they can compare images they take today with images that they took 100 or more years ago, because the lenses have never been twisted or changed their orientation. They get really good proper motion work out of it.
Yeah, so it still has some scientific value, and hopefully it will continue to be available for a good long time. So this is a picture of the objective, the lens up at the front. I believe the person on the left may be Hale, but I can't figure out who the person on the right is. Probably doesn't matter for the purpose of this presentation, but it gives you a sense of what a 40-inch lens looks like
one of the Clark brothers.
Could be. So the point being is that it's a very big piece of glass. And it is an achromatic telescope. So there's actually a second lens behind that. And this is all built around that. Now, there are some limitations to big refractors. Which is why we'll come back to reflectors in just a second. The obvious problem was manufacturing lenses bigger than 40 inches. I mean, they can manufacture pieces of glass that are 8 meters across, but remember that with lenses, you've got to account for multiple surfaces rather than just the primary surface on the front. And so it was becoming a little bit technologically challenging to do that. They probably could have if they wanted to, but the other problems was having a massive piece of glass hanging 100 feet above the observatory floor. This was problematic not only in terms of mounting it originally, but it also tended to flex the tube. So it's easier to have mass hanging from the bottom than it is from the top. And so that became a real problem because the tube would flex as you move the telescope around with that kind of weight. The other problem was the size of these things. You saw in this picture here just the size of the enclosure that they were having to build. Now, the enclosure is probably not the most expensive part of a telescope, but it is becoming some kind of a nuisance to have to build these, what were rapidly becoming somewhat smaller average size apertures for these huge enclosures and these huge mounts. And the mounting became a problem too, as we'll see. It's very hard to out-as mount a refractor because you're viewing it from the narrow thing from the end. And so there were that consideration as well. Much later, meaning the middle of the 20th century and later, there's another problem, which is that lenses which are transparent at optical wavelengths are not necessarily transparent at things like infrared. And so if you're building a very large telescope that's meant to be infrared friendly, you don't want to be using traditional glass lenses. That was not initially the reason why they switched away, because infrared astronomy doesn't start until the 60s or the 70s. And so that was not their original thing. The other thing about the thing is, although these things are very nicely shaped and the images are superb, chromatism entirely was not completely solved by the until the apochromatic refractors were developed, and they required fairly long focal lengths, and which meant slow optics. So once you get into that imaging era, there are certainly a lot of imaging that was going on, as Doug says, even to this day with these refractors, because again, they're very sharp, they're very precise, but not necessarily ideal for wide focal lengths. Yes, Doug.
Go back to the picture of the dome on the inside.
Yeah.
That one. So to give you an idea of what Stephen is talking about, the size of these domes, this dome here for Yerkes 40-inch refractor is actually larger than the dome for the 100-inch Hooker telescope at Mount Wilson.
And so you have to build these massive structures around the telescope in order to make the telescope work. And that becomes a major problem. I mean, it's not, as I said, the dome is probably not the most expensive part of the telescope, but it does become a nuisance.
There was one other problem with lenses larger than 40 inches. They sag.
Yeah.
You're only supporting the lens on the rim. And so when you're looking at a target that's close to the horizon, the lens has one shape, but then when you look up at a high angle, the lens actually changes shape because the glass sags.
Yeah.
Because you're not supporting it except on the rim.
On the rim.
You don't have that problem with the mirror because you're supporting it behind.
Yeah. So beyond 40 inches, they start to become impractical. And so what happens with that is in the late 19th century and early 20th century, there's a return to interest in reflectors. Now, reflectors never went away completely. It was just that for about 50 years there was a lot of interest specifically in refractors. By 1900, though, the limits of the refractor development had reached their ends, and big reflectors had been already been built, but there were still some challenges. One thing that's important to note is by this point, glass mirrors are replacing the metal. And that improves the optical quality. These things are more stable thermally, but how do you build a glass monolith that size? Now, for a 40-inch lens, that's a challenge. There's no doubt about that. But once you get beyond 40 inches of aperture, it becomes more and more of a challenge to create a glass blank that big, whether it be a lens or it be a mirror. And so it was doable, and they did it. But that was a technological challenge that they to this day are having to deal with. And since we're only going through Palomar, we'll only talk about the historic versions. But along comes George Ellery Hale. And he too is I believe, wealthy from a New York family that's fairly aristocratic with a lot of money. He did have some qualifications as an astronomer. He's actually best known as a solar astronomer, but he also had a lot of money to back himself up. And he was better known probably as an organizer for getting money together for these huge projects than he was as an astronomer. He was extremely influential at the Yerkes telescope. He helped the University of Chicago. No, he was a Chicago Baron. I'm sorry, he was a Chicago Baron. He helped the University of Chicago build the Yerkes telescope, and he then helped finance some of the other big telescopes that we're going to be looking at. So things about him. So the first big telescope that he commissioned was Yerkes. But he was already thinking about something bigger by then. Hale commissioned the mirror for what would be a 60-inch in California in 1894. Now, he moved out to California, and obviously observing conditions were better from California mountains than they were next to Lake Michigan, although the water has a stabilizing effect. It's much higher, and so he was able to start focusing his intention on California. The mirror he commissioned in 1894. It took 11 years to get the funding for the rest of the telescope. And he originally was turned down by both the Rockefeller and the Carnegie Foundations in building this 60-inch. After the success of his solar telescope on Mount Wilson and demonstrating that that was a fairly good site for astronomy, Carnegie put up $300,000 for the construction of the rest of the telescope. The mirror blank that he created was 7 inches thick and weighed 1,900 pounds, which was pretty impressive for the day. This is an image on the left of what the telescope looks like today. Looks a little bit different from some of our modern structures. The image on the right is the fun one. That was hauling this thing up the mountain. Mount Wilson did not have a paved road at the time. He had to blast a road through and then carry the parts up. And so this was at the time the biggest telescope in the world that he built. And of course, being Hale, he immediately was starting to think about something bigger. This is an image of the mirror with it polished. Interestingly, it's not a Cassegrain design. It was built to be a prime focus telescope and possibly images off to the side from the beginning. This is in its mount, and as you can see, it's mounted from the back. This was the era of monolithic mirrors. So instead of having like modern mirrors where you have multiple parts or you have glass honeycombs, these were big, heavy pieces of glass which were suspended from the back. And this is an idea. Let me take just a quick step back. It was a good telescope. It became really critical at the beginning of careers of folks like Edwin Hubble, who were using that in the next telescope we'll look at to study galaxies and the like. But he immediately began to think about something even bigger. And so the next step up was a 100-inch. The left shows the design of the 100-inch, and the right is the telescope to this day. He again. This is a telescope which Both these telescopes still exist to this day on Mount Wilson. They are limited in terms of their scientific capacity because of the compromise that he made at the beginning of their production, being that they are close to Los Angeles. And anyone who's been close to Los Angeles knows that Los Angeles puts out more light than most cities on Earth. And so they were used for several decades for legitimate research, including really critical research that Hubble did to identify Cepheid variables on nearby galaxies, which allowed him to come up with the Hubble law and realized that the universe was in fact expanding. And that generated a lot of interest at the time in astronomy and producing bigger and bigger telescopes. It was named after Hooker, who was the original donor for the telescope. He was not the only donor. Interestingly, Hale convinced Hooker, who was a Pasadena hardware manufacturer with a somewhat dubious reputation, to donate $45,000 to fund the mirror. But he had to find the funds for the rest of the telescope elsewhere. And while he had trouble getting the 60-inch mirror built, building the 100-inch mirror was a real nightmare. The first glass blank, which was built by Saint-Gobain, am I saying that correct? My French is terrible, appeared defective. You could not fuse one giant blank at that point in one sitting. You had to do it in 3 different steps with the molten layers building up over time. The problem was that the 3 layers didn't seem to fuse properly when they opened the furnace and looked down on it. And so Hale convinced the company that made the mirror, and this is a French company, not an American company, to create a second mirror blank. Well, the second mirror blank was cracked and had to be destroyed. It was not useful. Meanwhile, Walter Adams at Mount Wilson realized that the first blank could actually be used. This was after George Ritchie, who's of course known for the Ritchie-Chrétien telescopes, and his design had not quite been fired, but had been sort of not been received very well by some of the people who were working with him. And Walter Adams took over the project of grinding and polishing the mirror. Meanwhile, after several attempts, Hale was able to convince the Carnegie Foundation to donate $10 million to complete the project. And the mirror is 4.5 tons of glass. Interestingly, it is the original first mirror that was eventually ground down. They were able to figure out a way to polish it and grind it. And so that is the mirror that is, as far as my information shows, is still currently used on the telescope. So for a big mistake, it actually worked out okay. Because there was talk of building a third mirror for this thing, and that did not go through because they didn't need it. And this is a picture of the Hooker telescope today. The one on the right is a historical image. The one on the left is the image to use today. Again, Mount Wilson is used somewhat, but because of the light pollution problem, it's not considered a very good site anymore. Yes, Doug?
Yeah, it's not used much because the light pollution is
Yeah.
so bad. But interesting enough, though, you can actually now outreach activities. Yeah. You know how you can buy time on a couple of the telescopes on Kitt Peak? You could buy time at Mount Wilson and be a guest observer, and you can actually use the Hooker 100-inch.
Yeah, so that is an availability. They do use it for outreach, as many of these telescopes have been, and that is something that became available. I think the last 10 years is that you can now rent time on it. It's not cheap,
no,
and so
it's about $3,000 a night.
Yeah, so it's not a cheap thing to do. But if you want to rent out the famous Hooker telescope, you are welcome to do that. I would personally buy for $3,000 a nice Schmidt Cassegrain, but Cassegrain, thank you. Okay, Palomar 200-inch Hale telescopes. This is where we're going to end the conversation tonight. From 1948 to 1992, this was the largest regularly functioning telescope on Earth. And I'm not going to go into what the exception to that is on this presentation. I'll bring that into the next one. But this was the was a true technological achievement. This is the only one of the big telescopes that I've actually seen. Being from San Diego, we took several trips up there when I was a kid, when it was still one of the largest telescopes on Earth. And it is true that the pictures do not do this justice on just how massive this telescope is.
And
It was,
you can still say, by the way, it still holds the title of the largest single mirror, one-piece mirror
yeah,
telescope.
yeah. And so it was originally called the 200-inch. Today we call it a 5-meter,
Yeah.
because the large scopes switched over to the metric system when they became when the metric system became the standard in science. But it is approximately 5 meters. It's exactly 200 inches. And it has a very interesting story behind it. Hale originally contracted, so obviously with a telescope this size, there's two major challenges. One is the big telescope itself. The second is the mirror, and the mirror is a bigger challenge. Hale originally contracted with GE to produce a fused quartz blank. Fused quartz has very good thermal properties. The problem is they could, after months and years of playing with fused quartz designs, GE could not come up with a system that worked very effectively that Hale liked to produce the mirror. So they basically said, fine, GE, we'll forget about it. I'm going to go to Corning Glass. Well, Corning Glass had Pyrex. I'm sure all of you are familiar with that. It's the glass that's used in laboratory equipment. It has very good thermal properties as well, not quite as good as fused quartz, but it was something that was pretty stable. And one of the designs that they came up with was a rib back to it. So it's not quite the honeycomb mirrors that Roger Angel makes, but it's along the same very general principles. In order to create extra strength, they didn't make it as it was one massive solid monolith, but there are ribs in the back, which add strength and maybe take a little bit of weight off. The problem was that in order to produce this, you have to have ceramic pieces inside the furnace where you melt down the glass. And when they first did this, those ceramic pieces floated up into the glass, basically making a total mess and something that they couldn't use. Meanwhile, the second attempt almost failed when in this case, they found a way to get the ceramic to sit on the bottom, but there were scars that appeared on its surface. And so 2 inches had to be ground off the top of it, even before they could start shaping and polishing it, just to get these scars to go away. It's 65 tons of glass. It is a massive instrument and a massive piece of glass. It has 3 different points of focus. The original design, as I'll show you in a second, it was to have a primary focus. It also has, I believe, the ability, it is also can be used in Cassegrain focus, and I believe it has an azimuth capability, but I may be wrong about that. Hale died in 1938. And World War II delayed the construction significantly. The mirror had largely been built by that point, but the construction of the telescope was delayed. It wasn't until 1948, that last part is incorrect. It's still a functioning telescope. It just was the largest functioning telescope until 1992. So I forgot the word largest functioning telescope until 1992. It is still functioning. This is one of the few telescopes that is still consistently used for research. There is some talk for the last few years about possibly backing off of that. Caltech owns it, or at least operates it, and they have bigger telescopes. They were also a major partner in Keck, which we are not going into tonight, and there are still bigger projects they want to use. It costs a fair amount of money, and as anyone who's lived in San Diego can tell you, Palomar and San Diego are not necessarily the best site on Earth for observations. The reason they built it there was because it was relatively close to Los Angeles and because it was a pretty good site. It's not Mauna Kea. So
Palomar
that was
is still a pretty good site today.
Palomar is a pretty good site. You still have the light pollution problem from Los Angeles and San Diego,
but not as bad as Mount Wilson.
Not as bad as Mount Wilson. So it is still used every night, as far as I'm aware, for when it's clear to do observations. And they've recently, I believe, added some adaptive optics and laser guide stars and things like that to it as well. So it's still an instrument. It is, by modern standards, not not considered all that big. 5 meters is big, but it's not 10 or 8. So it's gradually headed towards obsolescence. But it is truly remarkable to look at. This is the mirror taken out of the back of the telescope. On the right is an image of it not polished or not without its coatings. As you get is not silvered, and it's basically what you can see is the honeycomb structure beneath it. Again, saves a little bit of weight and adds strength to the telescope mirror. It is, at the time, it was obviously the biggest thing that had ever been built and would be for many decades. The left shows what it looks like when it's silvered with the proper coatings on it, and it can be taken out and cleaned and recoated and put back into the telescope with that. This is, as I said, the pictures don't do this justice. This is like a battleship inside a dome when you look at it. It's just an absolutely massive structure. Some people think that the U-shaped piece is the telescope itself. It is not. That is the mount. It is essentially a fork mount. It's called it's not exactly a fork mount, but it sort of runs on the same principle. It's split fork. And it again is so precise that you only need a very weak motor to be able to turn it, because it's balanced so precisely.
Less than 10 horsepower.
Less than 10 horsepower to be able to rotate this telescope. And so as you can see up at the top is what was called the cage. Today they have a secondary mirror up there, and it focuses primarily to the back end where the instruments are located. Originally, though, this was primarily used in the prime focus cage. So when it was originally built, you had to climb up into the top of the telescope when it was rotated sort of down, and you would ride there all night long. I'm assuming some people probably, it would be difficult to get in and out, and they would guide it from the top of the telescope. So the image on the right shows an astronomer actually doing this. There was an automatic guiding at that point, and so you would stand in this little cage, huddled up all night in the cold, guiding the telescope with your camera essentially fitting on the front end, taking photographic plates. Now, by this point, photography was very much a part of astronomy, and so the Palomar plates are, I believe, still in existence and used for reference as well. The ones that are interesting are the ones that are used by the Wide Field Telescope, but we're not going to talk about that one tonight. That wasn't a giant telescope, but this one was used for several years and decades as primarily a prime focus instrument. Today they don't have the cage anymore. They retired that, and it's used either for a prime focus camera up at the top or with a secondary mirror that bounces images down to the bottom. But you can imagine this would have been a really interesting experience for the astronomers who did it. And we're not talking technicians. They actually put the astronomers up there at the front end. And that is all I have for this night. I just covered a lot of material in a long amount of time. Any questions?
That was a really good presentation, Stephen. Thank you for doing that. There's some cool things in there.
Yeah, I got a question for you. In the early days, how did they shape the mirrors?
The same way they shape them today. They grind them with a grinding tool. Although they used a large machine to do it, to do the circular motion. And then at the final stage, they would get down and grind them by hand.
Yeah.
And then how did they measure it to know they got it right?
I don't know.
That I believe it.
There's a way to do that. It's the same way that you do for a small mirror, but there's a way that you can measure the curvature and the focal length and everything.
People made mirrors for a parabolic shape for decades prior to these big mirrors being made. So they had ways to do that. I believe it's called a Foucault tester, and it's basically it doesn't use lasers like the modern system does, or like they do. Go ahead. There's
a book in our library called the Amateur Astronomer's Handbook. It's about this thick. This thick. And it's got a whole section on how to test a mirror to determine the curvature, the focal length, and everything else. And yeah, it's talking about the focal tester and some other stuff. And that's the same thing they do for the larger mirrors.
Yeah, and realize that happens today, the general shape was mechanically ground, so that it would have to be, you would have a large machine. It was shaped in the rough shape of a parabola, and it would grind the mirror until it was roughly the shape that you wanted it, and then
And you go in there and finish it by hand.
polish. It obviously did not have robots like they do today, but it was a major process, and you would take a lot of glass off of it when you were grinding it. It would lose all of its mass, but it would be a significant part to be able to do that. As far as I could tell, they did not have the spin system that
No.
Roger Angel used at that point.
Yeah,
There was
they got
no way
that today. That's what they do today to get a rough parabola shape.
Yeah.
Now they spin them while it's still molten.
Yeah, but in the day you couldn't spin a furnace like that and
No.
expect it to work very well. So it was basically they would have the general shape. You grind it down to a rough parabola
Yeah,
and then
and
polish it.
for the Mount Palomar mirror, they put in those honeycomb bricks. They're silicon bricks is what they are, essentially that structure that you see. And that's to reduce weight. And the main reason they wanted to do that, they wanted to reduce the weight a lot. I think they cut the weight down by like 80%. Because they needed to reduce the cooling time.
Yeah.
Because if it had been a solid glass mirror that size, Corning said it would have taken umpteen years to cool properly. And so they needed to cut the weight way down in order to reduce the cooling time.
Yeah. Yeah. So, also, I'm sure that the weight was also an issue in terms of what is the spin on a mount.
Yeah, and the weight was, of course, an issue for the mount too. But I think the main reason they were worried about weight was the cooling, because of a large piece of glass, solid glass, they said would have taken many, many years to cool. You can't cool it too fast, because if you cool it too fast, it cracks.
Yeah. Pete, question?
Yes, Stephen, you mentioned, especially when you got into the very large reflectors towards the end there, there are obviously, damage or mistakes done with the mirrors. I would take it, especially when the, large refractors and transitioning, the technology and the science associated, especially with polishing or grinding those mirrors, a lot of times, did your research show that it was common for mistakes to happen? And sometimes, some of these mirrors and some of these lenses may have been to, a number of attempts to get it right.
My understanding is that any big piece of glass carries a certain amount of risk when you try and make it or try and produce it. Alvin Clark and Sons were really masters with glass. Undoubtedly, they had problems, and I'm sure that some of those things had to be corrected or replaced. But they had ways to handle it so that you ended up with a piece of glass that works. Now, that doesn't mean that there weren't challenges. I didn't find anything in my research about specifically the lenses that we were looking at, but it was something where I'm sure that they had a few blanks that didn't work.
Yeah, by the time they got to making the large mirrors for like Mount Wilson and Mount Palomar, they pretty much knew how to cast large pieces of glass, not crown and flint glass. So they didn't know how to make those kinds of pure lenses, but they knew how to make opaque glass. Like, if you ever look at the Mount Wilson mirror that's in the Hooker telescope, it's soda glass. It's the same glass that are used in soda bottles. It's terrible optical properties, but for a mirror, you don't care about its optical properties.
Yeah.
You don't care how transparent. And for Pyrex, Corning pretty much knew how to do it. The problem they had on the first mirror with the silicon bricks was the metal bolts that they had used to hold the bricks down melted from the molten glass, melted the bolts, so the bricks floated to the surface of the mirror. And what they had to do to fix that was they had to have hollow bolts and pump air to keep the bolts cool enough so they didn't melt. And that's how they kept the silicon bricks in place for the second casting. So they were learning lessons as they went.
And one thing to consider is it did take 40 years to be able to figure out how to make a bigger mirror than what they ended up with. Now, the Russians had tried it. They were not terribly successful. They built a 6 meter about 15, 20 years later. It was never considered a very good telescope. But the next ones to come along would take another 40 years and major improvements in design of the mirrors, which we may get into in another presentation as to what they do for the modern ones. Even
Multiple
with
mirror segments.
multiple mirror segments and further development of the honeycombing, and remember things like the Subaru and the Gemini telescopes actually use meniscus lens or mirrors, so they're much thinner than the ones per unit of aperture than the ones that they use for the Palomar scope to save weight. But then there were all sorts of constraints that came into that because of keeping the mirror shape stable as you point the telescope. You had to have active optics, right? And that was a major problem, is how would you make a mirror bigger than what they had built at Palomar, and it plagued engineers and scientists for the next 40 years until they actually figured out ways to do it. And Keck, which is the biggest, of course, uses multiple mirrors. They're assembled together in hexagons, which is interestingly the same system they use on James Webb for similar reasons, but slightly different ones. In that case, they had to unfold the mirrors in order to unfold it in order to put it inside the telescope. Or inside the rocket top.
I've been lucky. I've either seen and actually used a couple of those large telescopes. I've looked through the 40-inch Yerkes, and I've been to Mount Wilson, but have not been to Mount Palomar. That's the observatory I've missed.
Yeah.
And I've seen a lot of the other reflectors. I've seen the 24-inch at Lowell, and I've seen there's a 20-inch Alvin reflector at the Naval Observatory in Washington.
Yes.
And I've seen that one, and yeah, I've seen a lot of these classic telescopes, and they're really cool. So, yeah.
Steve, the other thing I noticed too, other than the two early on ones you mentioned, I think were early 19th century, but after the mid 1800s, don't see much coming out of Europe. Is it just because it wasn't a good place? I mean,
no, I mean, there were telescopes being made at the point. They weren't necessarily
the large ones.
Not well, the big ones too, but not the biggest.
Okay.
So in fact, my understanding is that some of the ones in Europe are actually using Clark lenses.
Yeah.
And so Clark was considered so good that they became the standard for the generation. And so they would go to the Americans to get at least the lenses built and then ship them out to Europe to put on their telescopes. One of the things to keep in mind is that a lot of these early observatories were actually built in what are now cities. And one of the reasons for that is before electrical lighting, there was not as big a light pollution problem. In fact, there was essentially none. So you could build a telescope in the middle of Paris or London and have a relatively good nights on it because electrical lighting hadn't come along. Of course, once electrical lighting becomes a problem, then astronomers have spent the last 100 years trying to get away from lights. And unfortunately, that's a whole different issue. But that's become the plague of this generation telescopes too. Is it was something like Palomar. The site was originally pretty good. It was the lighting around it that became a real problem. And San Diego, interestingly, did introduce some lighting ordinances, not quite as strict as we have in Tucson, but it still wasn't enough. I mean, it's just a huge city, and Los Angeles is the other direction, and they were a little less generous, and so it doesn't quite work as well as it used to.
About 20 years ago, I saw an Alvin Clark refractor come up for sale, a 10-inch Alvin Clark refractor. It eventually sold for about $85,000.
They're practically priceless. Works of art. Clark and Son did make a lot of smaller telescopes too, and a lot of them are still out there. But they're practically considered works of art.
Good luck finding one.
And they're held in private collections, and the ones that are permanently, a lot of small what we now consider small observatories around the country still have these telescopes that are refractors. They weren't all kept in very good condition, so if you ever read Sky and Telescope, they have occasional articles about these things being cleaned up and restored. I believe they did that with the Lowell Observatory telescope relatively recently, where they had a major cleaning of that. But a lot of these scopes are now being restored because they are considered such classics of glass. The only catch with them is they were achromatic scopes. They were not apochromatics. So that we finally, that's a whole different issue. What an apochromatic is, they have multiple lenses instead of just the two. So they have much better color correction, but they're much more modern instruments. If you can ever find an Alvin Clark refractor for sale, that would be something. I don't know if we'd ever be able to afford that for the club, but that would be pretty awesome. Yeah, so to answer your question, they were building large telescopes in Europe. It's just that they tended to use American parts.
Very good. Thanks. Hey, and by the way, Steve, that was a great presentation. I think everybody enjoyed that. I thought that was fantastic. Very informative.
Thank you. Any other questions? All right, we're good to go. Thank you so
Okay.
much for your attention. That was a long one.
Going to stop there.